Hi, this is Andrea Hendricks. The objective of this video is to show you how to graph y is equal to cosecant x and y is equal to secant of x and their transformations. Let's begin with the graph of y is equal to cosecant x. Well, do you recall that cosecant x is really the reciprocal of sine x, right? So it is 1 over sine x. So if we know how sine x behaves, we can find out how cosecant behaves graphically. Well, recall that a fraction is undefined when the denominator is 0. So everywhere that sine x is 0, we are going to have a vertical asymptote of the graph. Well, I've actually drawn for you the graph of sine x because I think to do these reciprocal functions, it's best to start with the graph of the reciprocal, that is, the graph of sine. So if we know graph of sine, then we can figure out where sine x is equal to 0. Well, sine x is equal to 0 at where? 0, pi, 2 pi, negative pi, negative 2 pi. So we are going to have vertical asymptotes at x equals n pi, where n is an integer. So let's go ahead and draw those on our graph. Okay. Now, the other thing we want to look at are some key points on the graph of sine, because that will allow us to get some key points on the graph of cosecant. Well, we already know what happens when sine x is 0. We have a vertical asymptote. Well, the other key points on sine x are those peaks and valleys, if you will, the maximum and minimum points. So let's think about what happens when x is pi over 2. So whenever we try to find cosecant of pi over 2, we're really doing 1 divided by sine of pi over 2. Well, we know the sine of pi over 2 is 1. So for the graph of cosecant of pi over 2, we would have 1 over 1 or 1. So cosecant of pi over 2 is 1. Well, what about when we plug in 3 pi over 2? Cosecant of 3 pi over 2 is equivalent to 1 over sine of 3 pi over 2, but sine of 3 pi over 2 is negative 1. So 1 divided by negative 1 is negative 1. So whenever sine reaches a mountain or a valley, you're going to have a point that corresponds to the graph on the cosecant function. So we have points here at negative pi over 2, negative 1, negative 3 pi over 2, 1, and then if you go in the left and right in that pattern, you will get those peaks and valleys as we just mentioned. Now, do you remember what happens when you divide 1 by a number? 1 divided by a number, if that number continues to get big, it's going to be very small. Well, what is the thing about sine? Sine has a domain, or range rather. Sine x is between negative 1 and 1. So whenever we divide 1 by 1, we get 1, or 1 by negative 1, we get negative 1. But whenever we divide 1 by a number that's small, those numbers get big, and that's why we get these asymptotes, because as you get closer and closer to 0, the number gets larger when you say 1 divided by that, right? Like 1 divided by 0.001 is 1,000. So as our graph of sine gets closer and closer to 0, the graph of cosecant is going to get larger and larger and larger. And well, we can see that if we plug in a few points. Let's think about this. If we think about what cosecant of pi over 4 would be. Well, sine of pi over 4 is the square root of 2 over 2. So if we do 1 divided by the square root of 2 over 2, which is equivalent to the cosecant, we would get what? You have 2 over the square root of 2. But if you multiply by the square root of 2 over 2, that's simply going to be 2 on the square root of 2 over 2, which is the square root of 2. Well, the square root of 2 is approximately 1.414. So at pi over 4, you're going to have 1.414. At 3 pi over 4, you're going to have the same value. At 5 pi over 4, we're a negative 1.414 because our sign is a negative square root of 2 over 2. And the same thing happens at 7 pi over 4. And if you follow along and take the reciprocal of all of those sign values, you're going to get a piece of the graph that looks like this. So the period of cosecant is still 2 pi. But the easy way to do that is to know where the peaks and valleys of sine occur, and that's going to give you the peak and valley of the cosecant. Okay, and remember that sine is an odd function, so cosecant is an odd function. That is, the graph is symmetrical with respect to the origin. Okay, so this is the basic graph of cosecant x. You can get that on the calculator if you like. And to get it on the calculator, you can do one of two things. You can do 1 divided by sine x. And if we graph that, you'll see the graph that I have drawn. Or you can use this -1 power. Now the -1 there does not mean inverse, it means to do the reciprocal 1 over x. So if I wanted to use that key, I would have to put in parentheses sine x, close parentheses after the x twice, and then raised to the -1. And if you graph it, you'll see that I have the same graph there. Now again, you can look at the graph of sine x if that makes it a little bit easier. Put the graph of sine x in on your calculator, and you can see the correspondence between those two graphs. So let's look at an example of a transformation of that. If I wanted to graph y is equal to 3 times cosecant of 2x, the easiest way to do this is begin by looking at the graph of y is equal to 3 times sine of 2x. Okay? Now we know that this graph has a period of 2 pi over b, or 2 pi over 2, which is pi. We know the amplitude is 3. And we know that the period is going to begin when 2x is equal to 0, and it will end when 2x is equal to 2 pi. So it begins at x equals 0 and ends at x equals pi. Well, what happens between 0 and pi? Well, it has to complete a full cycle of sine, which will look like this, right? So we know that the graph of 3 sine 2x, at 0 it's at a 0, and at pi it reaches 0. The point in between at pi over 2, it reaches 0. Well, what happens in between? It reaches maximum and min, but this time our maximum and min is 3 and -3. So at pi over 4, it's going to have a peak of 3, and at 3 pi over 4, it's going to have a minimum of -3. So you could get the graph. Oops, supposedly going through those points would be helpful. Okay, let me do one more cycle just so you can kind of get a feel for it. Okay, and of course this continues right in that pattern. So if I'm trying to draw the graph of 3 times cosecant 2x. Now I know where to put in my vertical asymptotes because I know those occur at the zeros of the function involving sine. So we're going to have one at 0, at pi over 2, at pi, 3 pi over 2, and 2 pi. So remember what we talked about before with this. Sine of 2x tells me that it's going to make 2 full cycles of sine in between 0 and 2 pi, which is exactly what we see happening here. Now, to get the graph of, let me draw this in a different color. Cosecant now is going to be in green. I'm going to know at those peaks and valleys because whenever I do the reciprocal, I'm going to have a point here, right? Because think of it like this. I'm multiplying 3 times the reciprocal. The reciprocal would be 1, but 3 times 1 would be 3. Okay. And then the graph is going to have that same basic shape, asymptotic to those vertical asymptotes, reaching that maximum or minimum point. Okay. Now let's look at that on the calculator. So let me clear this out. Okay, I do want to draw the graph of 3 times sine of 2x. Oops, didn't mean to put that parentheses there. It automatically started that. Okay, just so we can get that in. My window is still the same from negative 2 pi to 2 pi and pi over 2. So at every pi over 2 multiple, you're going to see a 0. Okay. Now let's look at the graph of 3 times cosecant of 2x. So one way you can enter that is 3 divided by sine of 2x. Okay. So you have vertical asymptotes everywhere there is a 0 on the graph of the sine, and then these mountains and valleys in between those asymptotes. Do one more. Let's look at y is equal to cosecant of 2x minus pi. So again, you would start by graphing y is equal to sine of 2x minus pi. Well, our period is 2 pi over 2, which is still pi. Now our amplitude is 1 because we don't have a factor other than 1 in front of the sine. Now we know that our period is going to begin where 2x minus pi is equal to 0, and will end where 2x minus pi is equal to 2 pi. So if we add pi and divide by 2, we get that it begins at pi over 2, and it ends at 3 pi over 2. And again, what happens between those? It makes a full cycle of sine. So at pi over 2, 3 pi over 2, and in between it reaches a 0. And this time let's let 1 unit be every 2, one of those. So in between it's going to reach its mountain and valley. Okay. Oops. So what about the graph of cosecant of 2x minus pi? Well, fill in where there's a 0, fill in with a vertical asymptote. So it's 0, pi over 2, pi, 3 pi over 2, 2 pi, and so on. And then it's going to fill in with this other key point, and then draw the graph asymptotic to those vertical asymptotes in between there. And you certainly could continue this in both directions indefinitely. Okay, and there you have it. And you could enter that on the calculator as well, do 1 over sine of 2x minus pi, and you would get the graph. Now let's look at secant x. Well, secant x is very similar. The only difference is the graph, obviously, but it's a shifting of sign, so it's going to look basically the same. Secant x is what? 1 over cosine x. So secant x will have vertical asymptotes where cosine x is equal to 0. Well, I've drawn the graph of cosine, and we can see that there are zeros at odd multiples of pi over 2. So there's going to be vertical asymptotes at x is equal to pi over 2 plus n pi. So you can then draw your vertical asymptotes in. And then I bet you'll know what the graph is going to look like from there. Same thing's going to happen when we take the reciprocal of 1 or negative 1. We're going to get 1 or negative 1. So the graph is going to go between those vertical asymptotes. The period of secant is still 2 pi. And if you recall, cosine is an even function. So secant is also even, as you can see that the graph is symmetric with respect to the y-axis, right? If you fold it along the y-axis, you get a mirror image of itself. You can fill in with these points if you like, but if we plug in 0, 1 over cosine of 0 would be 1 over 1 or 1. If we plug in pi, 1 over cosine pi is 1 over negative 1, which is negative 1. If we plug in pi over 4, cosine of pi over 4 square root of 2 over 2, so 1 divided by that is going to be 1.414. And if we plug in 3 pi over 4, that's going to be a negative 1.414. And so you can see these points on our graph, 0, 1. At pi we have negative 1. Pi over 4 we have 1.414, and at 3 pi over 4 we have a negative 1.414. Okay? So again, you want to begin by graphing the cosine and then getting the secant graph from there. So we'll do one more example. If we want to do 1/2 times secant of x minus pi, what are we going to do? Well, we would look at y is equal to 1/2 times cosine of x minus pi. Well, the amplitude is going to be 1/2. The period is what? Well, the period hasn't changed. It's 2 pi over b, but b in this case is 1, so 2 pi over 1 or 2 pi. We know that the period begins when x minus pi is equal to 0, and it will end when x minus pi is equal to what? 2 pi. So that means that it's going to begin at x is equal to pi, and it will end at x equals 3 pi. Do you remember that pi is called the phase shift? So what's going to happen there between pi and 3 pi? Well, the graph of cosine looks like this, right? It begins up at 1. So at pi, in fact, you know what, I'm going to need to extend my graph here just a little bit. Let's see, so pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2, oops. Let me move that down a little bit. 5 pi over 2, and 6 pi over 2, which is 3 pi. Okay. So at pi, it's going to be up at 1. At 3 pi, it's going to be up at 1. 2 pi will be down to -1. And then at 3 pi over 2 and 5 pi over 2, it's going to reach its 0. So there we have one cycle of this cosine graph. Oops, you know what I didn't do? What did I not do? The amplitude is 1/2. So let me change that just a bit. Apologize about that. See, even your teacher makes mistakes. Okay, let's do over. So our amplitude is 1/2. So if this is 1, okay, so at pi it's going to be at 1/2. At 3 pi it's going to be at 1/2. 2 pi it's going to be at -1/2. Then it's going to reach its zeros in between there. Okay. So now if we wanted to draw the graph of 1/2 secant of x minus pi, we know where the asymptotes occur. Those occur when the graph of cosine is 0. And then the 1/2 and -1/2, we're going to have a point on the graph of this secant curve, and then it's going to be asymptotic there. Okay. Now if you wanted to do this on the graphing calculator, we can draw first of all 1/2, so I'll enter that as 0.5 times the cosine of x minus pi. And we probably want to change our window here because we had to go over to 3 pi to see a full cycle. So let's put in -3 pi to 3 pi. And we can still keep the change at pi over 2. And maybe we won't do our max and min, -8 and 8. Let's change that to -5 and 5. And graph. Okay, so there we see the graph of the cosine. Just confirm everything looks the same, right? At every pi over 2, which is every other mark, I'm going to have a 0, which I do. So now if I want to enter the graph of 1/2 secant of x minus pi, I can do it like this. I could just do 0.5 divided by cosine of x minus pi. And graph. Okay, so again, everywhere I have a 0 on the graph of cosine, I have a vertical asymptote. Everywhere I reach a peak or valley, I have a peak or valley corresponding to the graph of secant. Okay, so that's pretty much it for graphing cosecant and secant. The key is knowing those graphs of sine and cosine very well to be able to get these reciprocal graphs. So if you have any questions, please don't hesitate to contact me.